right. So without further ado, let me introduce, it's my pleasure to introduce Professor Nicolas Menicucci from the RMIT. And he's going to talk about phenomena in bandlimited quantum field theory. Nick, whenever you want, first yours, I'll give you a 5-minute warning.
Thank you. Yes, so hello everyone, and I'm grateful to the organizers for the opportunity to speak, so thank you for that invitation. This is some work that I've done. It's actually 2 projects that I'm going to be talking about. More recent work is with Achim Kempf and Dominic Lewis, who is a student at RMIT. Well, Achim's not, obviously, but Dominic is a student at RMIT. And I'll also be talking about some previous work with Laura Henderson, who recently graduated from the University of Waterloo. I guess I'm sorry, Laura, I'm not exactly sure of your current affiliation. I guess I should have put UQ up there. But anyway, we were at U Waterloo when you were working with me on this. So I've got some funders down here. And this is our research group, Kermit. So I want to talk about the paradox of space-time. So you may have seen this before in Achim's talks and others, but basically I like to talk about it like this, that all of our best quantum field theories to date are asymptotic expansions. They always break down at small scales. If we try to take them all the way to the limit of infinitesimal size, then we get infinities. Renormalizable quantum field theories are such that the large-scale features don't care about the details of the small-scale physics. So at their heart, all QFTs assume some means to regularize the field. So this could be strings, loops, etc. But it's compatible with a grainy space-time at the Planck scale. Exactly what that is not specified, and with renormalizable QFTs, it's hoped that the details of that are not important. Of course, we know that there are cases where they are important, but let's just focus on the ones where they're not. Point being, QFT, at its heart, at its conceptual philosophical heart, is a continuum approximation to something that is believed to not be a continuum in some sense. There has to be something that breaks down. Okay. So general relativity, on the other hand, is the exact opposite. So this assumes that space-time is a manifold, and by definition, their mathematical definition, manifolds are smooth at all scales, and this is why you get singularities in the solutions to the field equations for a black hole, etc. This is what general relativity assumes. So we have a conflict. We have a conflict between quantum field theory wanting what I like to call grainy, although that's not the only way to deal with it. Something weird going on at a small scale, and general relativity, which wants everything to be smooth. So we have this conflict that's happening. And of course, wouldn't it be nice if we had a way of describing space-time as being both discrete and continuous at the same time? Now, when I gave this talk at Oxford 2 weeks ago, I got some very skeptical looks, and for good reason, because this seems entirely paradoxical. But if you know a bit about signal processing, maybe not so much. So if we could do this, however, I'm jumping ahead. If we could do this, however, it might resolve or render moot some of the problems plaguing the interface of quantum field theory and general relativity. So band-limited signals and the Shannon sampling theory. So band-limited signals, this is just classical signal processing. So band-limited signals, by definition, have a finite maximum frequency, the band limit, B. If you have a continuous signal, like for instance a sound wave, and while sound waves themselves are not well, I mean, they're made of particles, so they should be, but we care about the sound wave between certain frequency range because of human hearing, so up to about 20 kilohertz. And so effectively, the signal that we care about is a continuous signal that has a band limit of 20 kilohertz. That continuous signal, the sound wave, can be perfectly reconstructed, not approximately, perfectly reconstructed from discrete samples, now a discrete countable infinity of them, but still, from discrete samples if they're taken often enough above the Nyquist rate to be via sinc convolution, as discussed next. So that means that band-limited signals are both discrete in terms of their samples and continuous at the same time, because both contain the same information. So a little picture I like to draw is this. So if you have recorded music, you've got sound samples that are taken at time interval, 44 kilohertz. So it's more than twice the Nyquist rate. And we can continuously interpolate in between and perfectly reconstruct the signal up to the 20 kilohertz band limit. And the way we do that is with the sinc kernel. So this is the normalized sinc function. There's a pi in there, and it's just sinc of x is sine of x over x, and it looks like this. Importantly, this can be considered the Fourier interpolated Kronecker delta. So I like to think of it that way. That's so we have a Kronecker delta at the integers, and in between we have a continuous interpolation via this. Well, anyway, this function has this properties, and I could go into more about it, but I will spare you those details at the moment. Okay, so however, importantly, with a bandlimited signal, the lattice that you sample on is arbitrary, and it can be changed at will to represent the same original signal. Now, I found this to be profound, and I've talked about this at a previous RQI South, I believe. But what this means is that if we take the original samples from a signal and we reconstruct the continuum signal, then we're able to take new samples. And so what this means is that the discreteness, or the ability to represent the signal discretely, is inherent, but with no fixed lattice. So if you think about all the models that assume, like lattice models for continuous stuff, they usually say, well, we have a lattice and that's a problem because it's breaking the symmetry. And it is, that's true. But in this case, we have a type of signal, band-limited signal, has a discreteness to it. It has a discrete representation, but the particular one that you pick is not prescribed. And in fact, you can switch between them. You can have an oversampled signal as well. So the discreteness is there, but it's not as rigid as a fixed lattice. So this brings us to band-limited quantum field theory. So the question that has been asked, and I believe there's a talk about this already, can we apply the Shannon sampling theorem to quantum fields? And the answer is yes, by some dude over here. Now, this is Akin Kempf. Most of you know him. So he has, I like to call it type 1 and type 2. So I'll get to that in a second. But there's two different types of this. And type 1 band-limited quantum fields postulate a field with a hard cutoff at a maximum momentum, the band limit lambda. So now some of you will already say, well, hang on, you can't do that. Down here, we'll get to it. But the field at this point is now simultaneously continuous and discrete. The bridge between the two is the Shannon sampling theorem. Now, the problem, of course, is that this breaks Lorentz invariance. So it's likely not to be fundamental. Now, why does it break Lorentz invariance? Well, because if you say lambda is the maximum momentum, and then you have someone zooming by a signal going at momentum with momentum lambda, then what's going to happen? Well, that momentum lambda is going to look faster than lambda. So you can't do it. Lorentz invariance is broken by this. So it's likely not to be fundamental. However, it does provide a nice test bed for some of the basic concepts. And so we're going to be using this. I'm going to be describing work that is based on this. And there's good reason to believe that a lot of the basic concepts here will still carry over when one considers type 2 fields. So the type 2 band-limited quantum fields postulate a field with a hard cutoff in the spectrum of the D'Alembert. So previously, the type 1 cut off the spectrum of the Laplacian, which is just the spatial part. This is the D'Alembert. So in flat spacetime, it's just this. This can be made Lorentz covariant by construction, but it's much more difficult calculations. And the plan is to eventually use this, but not today. So that's the framing of the problem. Okay, so what I'm going to talk about are what are the observable consequences of a band-limited quantum field of type 1? Well, the most fascinating thing that we found is one of the most fundamental, and I've already talked about, is this discrete continuous duality. But not only that, it's that there's more phenomena than one might expect that carry over from one domain to the other. So without further ado, this is a paper in progress with Dominic, who's a current honors student at RMIT, Akin, and myself. And the working title that we have is Quantum Lattice Models that Preserve Continuous Translation Symmetry. So this is going to be a figure that I come back to a number of times, so please don't try to take it in altogether. I just want you to focus right now on the bottom right and the top left and this diagonal line connecting them. So I'm going to introduce two concepts and I'm going to look at them in several different ways. And when I say I'm really reporting on work that was done by Dominic. So, and I believe Dominic's on the call today. So we have a lot of times when you have a quantum field like Klein-Gordon Hamiltonian, that's talked about in pedagogical textbooks as if you have a harmonic chain Hamiltonian, and you take the limit between the elements of the harmonic chain to go to 0, and you maintain the mass density and the tension. And in that limit, you get a continuum model, or that's what we claim. So this does work in the calculus sense, but this is the usual thing that we're doing, and we're not doing that today. So what we're doing instead, I'm going to start by looking at the Shannon reconstructed quantum field theory that is exactly equivalent in the band-limited sense to the harmonic chain Hamiltonian. So how does that look? Well, we're going to start with a harmonic chain Hamiltonian, which was here. So we start with this Hamiltonian. So we have a harmonic chain with, maybe I should have put this first. So animation is not in the best order, but just bear with me here. You can look down here, and what we have are just a bunch of balls on springs connected to each other. And each individual ball has some displacement, a quantum displacement, which we call Q sub J for ball J, and it has some momentum Pj, and so it has some kinetic energy. So this is just a classical model, which is how you start, which is kind of funny. You start with a classical model of sound waves, and you get a quantum field, but I digress. So we have a kinetic energy, and then we have the energy in the springs. So that's what this is. This is just the elastic energy in the springs between the balls. And we sum all this up, okay? Well, if we treat the displacement from equilibrium of each of these balls, we just declare by fiat that these samples are going to be the sample, these quantum variables we're going to treat as samples from a field. And we can do this. We just postulate a field that is reconstructed via the sync kernel from these variables. In other words, the definition of phi at a given point is given by sync interpolation of all the Qs. And that's totally fine because these are just harmonic oscillator variables, so you can add them all up and get some other harmonic oscillator variable. So that's what we have. So it turns out that we just plug this directly in, and we're sampling the field at some lattice point xj plus some offset for the +1 minus the field at the lattice point. And then over here we have the P field similarly interpolated to the pi field. And in this case, there's a unit change. Don't worry too much about that, but it's necessary to make everything work out. In any case, what you get is this middle line here. And what is represented down here, sorry, I'm jumping ahead. So then if we go down to the final line, what's happening here is there's a theorem for band-limited fields, which is basically just the, I think it's Parseval's theorem, that if you have because band-limited fields, well, let me just state it. If you have the sum of a product of two band-limited things, then you can equally well integrate over those two band-limited things. So in other words, this is a trick that involves going to Fourier space and then undoing the Fourier transform. You know, we're saying I have an inner product in this discrete Fourier, in this of these discrete functions. We take a Fourier series to do that same inner product using Parseval's theorem in the Fourier domain. And then we go back to the continuous Fourier domain and use Parseval's theorem again and say, all right, well, the sum of all these quadratic interactions here is actually the integral of all these quadratic interactions here. And this is a very powerful tool that we can do when we have quadratic interactions. So we can always do this. And what we see is that what was a nearest neighbor interaction at the lattice level, in that this yellow ball here is interacting with its nearest neighbor only, and there's no interaction further away. That locality in the discrete sense is not maintained, is not promoted to infinitesimal locality at the continuum. In fact, the interaction is between the field point and another field point delta x away. Kind of what you'd expect, but anyway. Interesting feature though is this is translationally invariant. Take a moment to realize that even though this is interacting the field with itself delta x away, it's all possible interactions, not just the ones on the lattice. So we took a lattice theory and we promoted it to a continuously translationally invariant theory that has the same content as long as phi is band limited. Okay, so hold that thought. What we've done is this. And if we zoom in, I just zoomed in from the previous one, and this is what we get. We get the harmonic chain Hamiltonian. We have local interactions from the momenta. We have nearest neighbor interactions from the positions. And through Shannon reconstruction, we have a quasi-local interaction in the phi field. It's not local, it's actually distant. And we still have local interactions with pi. So we've lost the exact locality, but anyway, we have a continuous field and it's translationally invariant. All right, let's go and look at the other side. Let's look at the Klein-Gordon Hamiltonian. So we'll start with that in the continuum, and then we will sample it down to the discrete level. And this is what we get. So we start with Klein-Gordon. I think there's a typo on one of these slides. So one of these has a mass and the other one doesn't. It's not that important because this is also a quadratic term. So it doesn't, what I'm saying still holds. So we have pi squared, we have the gradient of phi squared, and we have m squared phi squared. Okay, so what we can do is we can do integration by parts and turn this into a Laplacian. That's fine. So now phi of x is interacting with the Laplacian of x second derivative. But the next step here may look a bit mysterious, but you can actually derive it from the fact that we are declaring, we are assuming, and I should have said this here, that phi itself is band limited. So that's always the assumption in what I'm talking about here. So the phi field is already band limited. And as such, there is, because it's reconstructed from discrete samples, the only functions of which you're taking any derivatives are just sinks. They're just displaced sinks of different heights. And all you have to do is just add up the contribution from all those sinks. And what you get is this. So we can actually replace this this calculus-based derivative with not just a nearest neighbor approximation, but actually an approximation that involves all of the other phis, because this is a displacement operator. So this is saying take the original phi and actually displace it m units to the right. And so we have an interaction between the phi at xj and the phi at j plus m, m times delta j to the right. And I'll show what this looks like in just a second. But if we take this formula now, and we treat the phi at the various lattice points. Remember, this is not a real lattice. We're just declaring I'm going to sample it at some lattice. So we sample it at some lattice, and we can do the same trick. We went from an integral to a sum, and now we can treat the phi at xj as a qj. We just say there's an equivalent model. There's an entirely equivalent model, which is this. There's some balls connected to each other via some sort of interactions. They're not exactly springs, but there's some sort of interactions, but it's long range. So it still has a momentum term, but now there's a self-interaction term. Well, there's a mass-ish term here, as well as a regular old mass term here. And now this is the key part, that each one of these oscillators interacts not just with its neighbors, not just with its second neighbors, but with all of its neighbors, with a strength that goes down as 1 over m squared. Now, if it were 1 over m, we could model this with electromagnetism, but it's 1 over m squared. So we haven't figured out what physical system this corresponds to yet. If anyone has ideas, please do let me know. But this is the Hamiltonian that you get, and this has the same dispersion relation. This is actually a lattice model, an exact lattice model of a band-limited Klein-Gordon field, free field. Okay, so what we've done is we've started with a Klein-Gordon Hamiltonian. Oh yeah, the mass term is missing here. We have local interactions from the phi field in the form of a derivative, and we have local interactions from the pi field. And when we band limit and sample, again, we've lost locality, because now what used to be a local derivative just at this point now involves all of the other points. And that's because while the sink acts as a Kronecker delta in its value, its derivative is nowhere zero except at its center. All the other derivatives are non-zero. So every other point, when you're taking a derivative of a band-limited field, you're going to need the contribution of all of the other points in all of the other samples. So that's why you now have an infinite range interaction. Okay, so what we have, so this is the story now. Instead of going directly by taking the lattice spacing to 0, we can now have a translationally invariant Hamiltonian, continuous Hamiltonian representing the harmonic chain, and we can start with the translationally invariant Klein-Gordon Hamiltonian and represent it as a lattice model. So let's look at the top line there. We have these things that are continuous and translationally invariant. Well, if we have continuous translational invariance, then the total field momentum should be conserved. This is the total momentum operator for a quantum field in 1 + 1 dimensions. And it should be conserved, and we've shown that it is. Dominic has shown that it is. So in fact, what we do is we can replace the derivative with respect to x here with the band-limited derivative. In other words, if we expand phi in its sinc interpolated form from samples, then we can replace it with a sum of all of the samples in phi. And we actually get this operator when we now go from the pi, we treat the pi field, which was here, we're doing a bunch of tricks. So we have the integral of a product of two things, so we can replace it with a sum, and then at sample points. And then we treat each of these samples from the field as if they were
and it's Nick.
5 minutes until what? The end of the talk or the end of the session? Because we started 5 minutes late. What are we doing?
The end of the talk. You'll be in time. Yeah. You have 5 minutes more to talk.
I have 5 minutes more to talk. I'm going to take a little more than that because we started 5 over. All right. So so this is actually this is actually so that the pi, yeah, right. The pi here is actually p, and the phi is this q. All right. So the upshot here is the total momentum operator generates continuous translations, continuous displacements in the field. In the discrete version, these displacements are interpreted as first interpolating to the continuum, then displacing, and then resampling. And that's what goes on. I think of it as like, you're looking through a tall picket fence and you're watching someone mow the lawn from behind. And what do you see? Well, you see colors changing in the picket fence, but you can kind of make out that there's something moving behind it. That's the picture that I have in mind for this. But what's interesting is that any discrete translationally invariant Hamiltonian, when you have like a lattice model, when interpreted as a sampled continuous Hamiltonian, conserves this momentum. Actually, oh shoot, I don't remember if this is, ooh, that's important. Dominic, if you can tell me if that's quadratic or not. I don't know whether we ever solve that. We will solve this before we post this paper. It's either any one or it's quadratic Hamiltonians. I don't remember which, but certainly the quadratic ones. Any lattice model that is discrete translationally invariant, we can interpret as a continuum, as the samples from a continuum model, and we actually have this conserved total momentum, which is representing a continuous translation. All right, so brief review of some results that I did with Laura. So I don't need to tell you guys most of this, so I'm actually going to jump through this. You guys know what relativistic quantum information is. And if people are watching on the video, you can pause here. And most people know what unreduced detectors are. In fact, one of these guys is here. And so, but the point is that we have a qubit that is rotated in its, undergoes a Pauli rotation with a strength given by the field at the location of that, where the qubit is. We assume that there's some ability to control its interaction strength with the field, and there's an overall coupling constant, which is assumed to be small usually so that we can do perturbation theory. So we use this to do entanglement harvesting. Again, most of you have seen this, but I will just flash up some slides to show you how I like to discuss this with people who have never heard of entanglement harvesting. So I think this is actually an important thing to do, because when I gave this talk at Oxford, there was a lot of skepticism about how a quantum field could be entangled. And I've had this in every other field other than RQI. Sorry for the pun on field, didn't mean to. So if we have the ground state of two uncoupled oscillators, we can represent it in the local modes, or we can go to the normal modes, even though there isn't any connection. And we still have this because the frequencies are the same. The frequencies of the breathing mode and the center of mass mode, when there's no coupling, are the same. So this is both a tensor product. But when you have any kind of coupling, that's no longer true. It's separable in the normal modes, but not in the local modes. And it takes people a while to wrap their heads around this if they haven't seen it before. So then, of course, the question is, can you actually see this? And the answer is yes. If we attach local detectors to these things, we can actually harvest entanglement from that is here. So this tensor product is not the same as this tensor product. That's what it means. Okay, so then we just do the usual trick where we extend these oscillators out to be a quantum field. Again, going back to the usual thing. And so we say detectors should be able to harvest entanglement. So since you guys have seen this, I'm just going to go very fast. So the vacuum is entangled. It's true for all fields. And this entanglement can be harvested. So this was shown by Benny Resnick in 2002. And again, if I'm going too fast for those on video, please just pause. And we can violate a Bell inequality with this in principle. And it can be used to distinguish a heated universe from an expanding one, even though a single detector can't do that. That's what I showed in 2009. That was what Edo mentioned earlier. And it's sensitive to the motion of the detectors, as we showed in this paper in 2015 with acceleration. So what are the consequences of a band limit on the field in terms of entanglement harvesting, as well as other topics? So band limited consequences. So this is in this paper that we published in late 2020, Laura and myself. Point-like detectors do not exist. I've got 4 more slides. I've got it, Eddie. Any attempt to couple to a localized field point will actually couple to a delocalized mode with the shape of the reconstruction kernel. So that's one result. There's 2 more results. So we try to couple here and we end up coupling everywhere here if the field is actually band limited. A second thing is that because it's band limited, if you have an atom with a very large energy gap that's close to the band limit or even over it, if that's possible, then there are fewer field modes for it to decay into, and that actually prevents the particle from decaying. So you get a reduced particle decay probability. This is what it would normally be if you had no band limit, and then as you introduce a smaller and smaller band limit, so the yellow, then the blue, then the red, then this probability drops down to 0. In which case, there's nothing for the atom to decay into. And finally, we can harvest entanglement at regions that are normally forbidden. And that's really interesting. So you can get separation between these detectors, but because of the long tails of the sink, you can actually harvest entanglement beyond the maximum distance where harvesting would be possible without a band limit. And this could be used, at least in principle, to detect or measure a fundamental band limit. So what's shown here is that the negativity in the 2 detectors, the 2 qubits that are interacting with the field, in the absence of a band limit, it's 0. And then when it has a band limit, this is what you get. And sigma is the time that the detector's on. Okay, so the consequences of this are point-like detectors don't exist, reduced probability of de-excitation, and harvesting at normally forbidden distances can be used to detect principal band limit. So in conclusion, general relativity assumes perfectly smooth spacetime, continuous. QFTs assumes some sort of graininess or some sort of feature like that at small scales. Band-limited quantum fields are both continuous and discrete at the same time. And this maybe can help resolve some of the GR-QFT inconsistencies. Provides a duality between discrete lattice theories and continuous ones, including preserving continuous symmetries even on a lattice, which I find fascinating from a philosophical point of view. Bandlimited quantum fields have observable consequences for single coherent detectors and multiple ones harvesting entanglement. And everyone is invited to come visit the Kermit lab at RMIT. Thank you.
Thank you, Nick. All right, we have time for one question. Laura, go ahead.
Yeah, hi. That was a good talk. I just have a question. Do you think if you say demanded that you had this sort of continuous translation symmetry that you would get the band limited quantum field or the band limited theory? Like, I'm wondering if there's something about uniqueness there.
I don't know, because I mean there's no unique definition of a continuous translation of a discrete object. So we know that if we have a continuum quantum field theory, whether or not it's band limited, it conserves the field momentum, total field momentum. So if you start with a lattice theory, you have to define a notion of continuity before you can say whether the P is actually conserved. If that doesn't answer your question, maybe you can rephrase it, because maybe I didn't get it.
No, I think that did answer my question. I'm just wondering but I guess I can, at least to another question is there something sort of minimal about your definition of continuous in that sense?
Oh,
It's just because there's a lot of ways of discretizing a field, and depending on how you do that, you can get different properties. So I'm wondering if there's something special about this, perhaps in the notion of continuous.
That it might be, in the sense, so that there is something unique, or maybe not unique, but certainly special, which is in the way that we are in this band limited approach, in that you see that this particular choice for the approximation to the derivative, the second derivative, is not actually an approximation. This is exactly the second derivative of the continuum as represented in the lattice model. And the dispersion relation of this is exactly the same as the Klein-Gordon dispersion relation, relativistic, perfectly flat relativistic up to the band limit. So in that sense, it is unique.
Okay, yeah. I
Right.
think that answers my
Good
question.
Thank you.
All right, thank you, Laura. There's also a couple of references I think Jose is going to put on Slack about, you know, Dan Grimmer has written a couple papers about this precise
He did,
question.
he did.
So
Yeah, he looked at it in classical. We had some chats with him. Yes,
that's
absolutely.
right. Yeah. Cool.
Very good work.
There's no problem. There's also maybe one more last comment. It's true that we know about this harvesting phenomenon from Benny Resnick, right? But just to mention that I'm pasting something here that 10 years before him, even though of course we didn't see it, Anthony Valentini already discovered it. So anyway,
yeah,
very good.
You're right. I probably should have put that one in there. Thank you.
Oh, no problem. Okay, Nick, thank you very much for your talk. Let's thank Nick again.